here's a challenge for you. Can you define the notions of continuity and convergence on a set without actually having to define a metric or a measure? So without it converging, for example, without it converging in metric or in measure, it still converges in another sense. So the most simple way to do this is if given a point X, we can draw an open neighborhood, but for now just a neighborhood. We'll get to the former word once we construct a formal definition, but and then a sequence of points which we collectively call xi. So xi all the way up to xn for some natural number n. So we collectively call this sequence xi for I in the natural numbers. And if for I greater than or equal to n, we'll call this neighborhood U. Xi, all the xi's past that point are element of the neighborhood. Well, if we make this neighborhood sufficiently small, or all of the boundary points are sufficiently close to x, then it becomes infinitely close or arbitrarily close, sufficiently close to x, and we can define the notion of convergence in this way with open sets, okay, or with neighborhoods. So what I want to address next is what desirable properties should, if we were to define a collection of open sets on a collection of sets which satisfy specific criterion, then what should we have that criterion be? So again, I've got my point X, but this time I've got two open neighborhoods, one of which contains the other around X. And what I want to address first is should this collection of open sets be closed under union? And if so, what kind of union? Finite union, countable union, or arbitrary union even. So basically what we want to address is U1 union U2 open. Well, this is an easy question to answer because U2 union U1, obviously, since U2 contains U1, is going to be U2, and U2 is an open set, so hence we've proven our condition. So it is indeed closed under union. If we moved U2 into here and had countably or even infinitely many, arbitrarily many elements in this sequence, then it's still going to be an open neighborhood because there still has to be a biggest neighborhood. No matter, there still has to be a biggest neighborhood. And even if they were equal to each other, if they were all equal to each other, similarly, the union of something with itself over and over again is just itself. So hence we can say that it's closed under arbitrary union. It doesn't matter if it's finitely many values in the sequence or infinitely many. So hence we can conclude that it's closed under arbitrary union. So now let's address intersection. So the question now is U intersect U2 open. Now once again, this is easy if we have countably many. So this shaded area here is going to be the area in question, and of course this should be, well, we don't know that yet, but so this blue shaded area is U1 intersect U2, and well, what does this consist of? Fundamentally, consists of all, well, what is U1? It consists of what's in U1 and U2, but what's in U1? It's all the values that are sufficiently close to X according to U1, or U1 sufficiently close to X, and similarly, in a similar way, for U2. So basically, it's all the points that are sufficiently close to X by the nomenclature of U1 and U2. So consists of all points sufficiently close to X by the nomenclature of U1 and U2. So it's this shaded area here. But it doesn't matter what the nomenclature is, it's still sufficiently close in a way, so hence we can conclude that for countably many of these, for finitely many of these, it's closed under this operation. But here is where the problem arises. So, once again, x, u1, and, well, here, I'll make this a little better. I'll make this u1, this u2, and then, all the way on to u infinity. So we've got a sequence now, an infinite sequence of these. But if we take their intersection over all I, what's that going to be? Well, once we get smaller and smaller, it's going to get infinitely close to x. So, of course, the intersection over all of this is going to be x. And because it excludes everything, this isn't an open interval. It's an infinitely small open interval, but we can't really have that. So, to make this more concrete, allow me to show you another example of this. So I'll take the real line, centered at 0, 0. So take the sequence of intervals of 1 minus 1 over n to n. And in the natural numbers. Let's take this sequence, or here, there's probably a little better way to write this. So let's take this sequence here, and okay, we'll start out at 1, so 1, negative 1, 1, 2, 1, minus 1, 2, and so on. And taking their intersection, once again, we're left with the center of all of these. So I'll just call this, I'll call this the I. That's not a good idea. Well, actually it is, but I just used the wrong index. I'll call this I of n. I of n. Once again, is a set containing 0, right? Just the one element set 0. For a similar reason, it's going to get infinitely small, and then once we take their intersection, it's all going to go back to 0, right? We could do the same thing for balls or hyperspheres or whatever you wanted to do, right? So this is a huge no-no, as we've shown twice. Whoa. Hence, now we have all of the desirable properties that we need to define this alleged collection of open neighborhoods. So what we call this is a topology. So we say that tau forms a topology on X if 1, the empty set and X are in tau. So we're just setting, first of all, we're setting an infimum for what we want the topology to be, and here it has to contain X because, of course, all of the open intervals contain X, and then we take the union of all of these. Collectively, all of these points are X, and if all of them contain all of the X's individually, X has to be an element of tau, right? Now, the two properties we discussed, for some sequence u of I, some sequence ui in tau, their intersection, their countable intersection Here, I should write this better because it's not all natural numbers. All the UI is a collection of sets is in tau, as we showed, or motivated at least. So for UI, I should write this better. U alpha, alpha, and A. So we're just using A as a placeholder. It could be infinite or finite in tau. Then union of alpha and A of all the U alphas is in tau. So now, as I previously motivated, let's see how we can define formally the notion of convergence on a topological space. A topological space is just a space equipped with a topology. So, let's draw my diagram, and then once again this sequence of points xi, and this is xn. So the definition should be, we say xi, a sequence of points, I the natural numbers, converges to point x if there exists an n in the natural numbers such that for I greater than n, xi is in U for some open neighborhood U around X. So this makes sense. If we make this the boundary point sufficiently close to X, then we can make this point sufficiently close to X, and then all of them will be inside of that neighborhood. Okay. So this is convergence. Now what about continuity? I haven't really talked about that at all. So we say f from x to y, where x and y are two topological spaces, is continuous if for some open set contained in y, the preimage of U is open in X. So let's take some examples. So with the discrete topology, which is the finest topology or greatest topology, so it's just equal to the power set of X. So for example, take X as 1, 2, 3, the set containing 1, 2, 3. So we got 1, 2, 3. Then all of the possible subsets, we've got 1, 3, 2, 2, 1, 1, 3, 2, 3, and then of course the entire set itself by definition, because that's a requirement now. These are all the open sets, so literally every subset possible, and it contains every other topology because every set on the space is an open set. So then some map from f to x from y for some topological space y, then the preimage of any set in y is going to be open because any possible preimage, any possible set in x is open. So hence this checks as continuous. Then the trivial topology is the exact opposite. It's the weakest topology. It's contained by every other topology. So this is going to be a lot easier to draw. It's just nothing. Well, it's not nothing. It's just X and the empty set. It's the minimal requirement for a topology. It's kind of like an excuse. So contains 1, 2, 3, and the empty set, but that's it. Okay, so of course there are only 2 sets in X, and both of them are open, so this also checks it's continuous. Now it's going to be your little homework to prove that this aligns with the definition of continuity in metric spaces, and if you want, you can post that in the comments or email your solution to me. But that's going to be your little homework. Now, as a last thought, let us consider Euclidean space. Okay, so every open, well, first of all, it's a topological space because it has a topology induced by the Euclidean metric. So it's got what we call the Euclidean topology induced by Euclidean metric. So turns out, as you may know, that every open set in Euclidean space can be written as the finite union of balls. So take an open set. By the way, the reason I've been drawing them with no boundary this whole time is because in Euclidean space, or in Rn, they're just spheres. Open sets are just are sets without their boundary. Similarly, closed sets, which are the complements of open sets, are the sets that have boundaries. Okay, so just for some intuition in connecting it to more familiar spaces, because what we've been doing so far is very abstract. Anyway, so we've got some open set, and it can be written, well, these got to be open balls, but written as the finite union of countably many open balls like this. And of course you get the idea, just countably many open balls. Okay, so in metric spaces, not all sets are created equal, so it's useful in any other topological space to have these sets which kind of form the basis for the entire topology, in that we can construct the topology from the basis, and every open set is the finite union of the open sets in the basis. So then, with that, let us define the basis of a topology. So we say a collection B, a subset of tau, is a basis, or I should say forms a basis, for the topology of X and if the topology on X is well understood, then we'll usually leave this part in parentheses out. If it's all of the elements of B are open, but if it's a subset of the topology, then obviously all of them are open. And if any element of tau is the union of countably many sets in B. So and of course any element in B can be expressed as the union of itself and itself. So this holds for elements of B as well. So because this video has gone on long enough, I'll leave it there, and I hope that I've given a comprehensive first introduction to topology, and we're going to start with manifolds very soon as soon as we get all of these topological definitions out of the way, and I hope that I'm able to motivate them well. Anyways, I hope you enjoyed this video, and yeah.